So hopefully everyone can see this fine. As Lisa said, I'm Tim Madden. I've been involved in making printed circuit boards since the late 80s and involved with a couple different companies as well as several companies in their design departments. So I've been on both sides of the fence with this. And laminates have been a kind of constant issue of talking about, and everyone seems to have their favorites and no real right or wrong one. But the more you learn and understand, and that, then you can pick the best one for your particular design or your applications. Got a couple topics I'll go over. Each of these is really, anyone that knows anything knows that it's a very broad topic, and probably could talk. You can go to Arlon or Nelco, and they can have probably an hour presentation on just any one of these things. So we're going to go over the properties, all the different suppliers, the different types and families of materials that we're all thinking of, and how to choose and call them out on your print at the very end. I'm only going to be talking about rigid boards, not flex. So what we're doing is dealing with two types of things. One is the core material, which is made up of the glass fabric, resin, and prepreg that have been pressed together with copper foil on top. The different thickness of a core will be made with different styles of prepreg and will vary in resin amount. So there's not one way that a particular thickness was made. The prepreg, of course, is the glue that is used to press the different layers together once we've imaged your board as we're making a multi-layer board. These also have different glass styles and resin contents and different thicknesses resulting from them. So that's a really 30-second view of how the laminates are made by the different suppliers of them. A couple of major different properties that we'll go over that we all think of, both electrical and physical characteristics. You go to a supplier's web data sheet with their materials. They'll have a whole page listing lots of different properties. You'll have to decide what is most important for your particular design. These are kind of the main ones that people talk about in different situations and the primary ones when selecting their board. First one is the glass transition temperature. This one is talked about a lot. This is, or T sub G as it's also called. This is when the material goes from a rigid state to a rubber one. Doesn't mean it's melting or anything like that. It just becomes very more pliable. You obviously want higher for lead-free applications, and higher is also better for repeated rework. Rework is always another issue. There is no hard, fast or rule numbers. Going through this, when I was in aerospace, this seemed to always be a constant source. Like, okay, how many reworks can we do? As we take and replace components constantly. Over the years, I think there's been a lot of papers done, but there's been nothing to say, okay, a glass transition temp means this number of reworks can be done. With lead-free, you want 170 degrees or higher. And the glass transition temperature has kind of become the standard for reliability, as that is what the thermal, at that point is when the thermal rate of expansion goes to the highest level. And the one we talk about most and is called about for when we do lead-free applications. Next property is the decomposition temp. This is when the resin actually starts to break down, burn up, or whatever it is. The decomposition temp is about when 5% of the resin is lost. So obviously, once again, you want much higher for lead-free applications, and it will also be much higher than T sub G. So for instance, for lead-free, when people talk about that, they want higher than 340 degrees. This is kind of the point where you really want to avoid submitting your board to. So you want to make sure that if you're dealing with some high temperature or some extreme environments, that the decomposition temperature is much higher than what you're dealing with. All then these relate to the CTE, the coefficient of thermal expansion. all materials expand as they get heated, whether it's plastic, air, water. The molecules get further apart as the temperature rises. So the coefficient of thermal expansion describes the number or percentage of how much the material expands as it is heated. The glass transition temp is kind of the magic number in this case because it's a linear progression. It expands at the same rate. But once you go over the glass transition temperature, the CTE becomes much larger. So you'll have two coefficients of thermal expansion, one for less than the glass transition temperature and one for more than it. The other thing for this that you want to worry about is a mismatch between the components and the board itself. So the obvious example is silicon chips have a very low CTE. And if it's much lower than the board and the board is heated, the solder joints, the board will expand faster than the component, and then the solder joints can weaken and break. So you have to look at your components as well and how they act if you're submitting your board to some pretty high temperatures. For electrical considerations, dielectric constant seems to be the one that we talk about the most. This relates obviously to electrical characteristic and is used in impedance calculations. A rough definition of what the dielectric constant is it's the property of a material that impedes the transmission of electromagnetic wave. The lower the relative dielectric constant, the closer the performance of the material is that to air. The property is critical to matching the impedance requirements of certain transmission lines. When you look on a data sheet, they'll give a value, so like FR4, they usually say 4.2 is the number we use for the dielectric constant. This really is in reality a range because the exact value will vary within it, depending upon copper thickness, varying between the copper itself, the thickness of the laminate, as well as how it's made. So in the bottom below, I have different pictures of fiberglass weave where 7628 has a much bigger weave, all very tight together compared to a 106. This has a definite effect on the dielectric constant. For calculations, it's easiest just to use one number, so 4.2 is what I use for FR4. But when you start to really dig into it, you discover that a 5-core FR4 will have a very different dielectric constant than an 18-core. Roughly, it's about plus or minus 0.5 within the family. The dielectric constant is also very dependent upon the exact temperature and the frequency used within the design. So if it's a high temperature, you'll have a different dielectric constant. Just like if you're using higher frequencies in your design, the material will respond differently to those frequencies. As I said, if you look at a data sheet, there's a lot of other properties. Some of them are the dissipation factor. This is another one that's commonly referred to as. This describes how much of the energy transmitted is absorbed by the material. The greater the loss tangent, the larger the energy absorption into the material. This can be important because the property directly impacts the signal attenuation at high speeds. So if you're dealing with high speeds, you might want to look at the dissipation factor of the given material. Moisture absorption is more of an environmental factor, and that's the tendency of a material to absorb moisture from the surrounding environment. This will also then affect its other properties like the dielectric constant and the glass transition temperature. There's some that absorb very little water, and then others like polyamide that really seems to suck it in there. UL rating is the laminate flammability. UL just stands for Underwriter's Laboratory, and that's kind of pretty much every material has a different rating. Time to delamination. There's a time to delamination at different temperatures. Usually there's two numbers for this. 260 and 288 are the most common used. All that is showing is what is the time until the material starts to delam, come apart at that given temperature. Obviously, if you're submitting a board to some very high temperatures and you see a very low time to delamination, you might want to reconsider the material usage for that part. Huge variety of suppliers. At Royal Circuits, we use all of these: Isola, Rogers, Nelco, Arlon. Arlon is now part of Rogers, so they've kind of merged together. They're still two separate divisions right now, but we'll see on how that changes. Panasonic, we get Matron material from them. DuPont. They're also, each of their, even though they'll have equivalents, they'll have very different ranges within there. FR4, so now we'll talk about all the different families or flavors that we refer to. FR4 is probably the most common that everyone talks about. That just refers to high temp that's done for lead-free applications. Or I mean, FR4 just refers to flame retardant, and it can range from very low flash resistant temperature that's not suitable for lead-free applications to much higher ones like to 370 HR. So you want to be specific on the type when you're calling out your board. So if you're calling out for lead-free, you want to specify a T sub G of 180, or even just specify on the print to say this must be suitable for lead-free applications, and we'll know what that is. At Royal Circuits, all our multi-layers we do on high temp FR4. The only time we'll use low temperature that's not good for lead-free is for double-sided, and it's the print specified. I said isn't required. High-speed materials. These often have a lower profile copper because that has been shown to have better results. This is one of the traits of a high-speed materials, that they'll have the low profile copper used with it. Dissipation factor and decay are very important, but there's not one exact number that's perfect. And especially, as I talked about earlier, it'll vary within the part. So it is, the dielectric constant is very dependent upon how the material is made. When we do our impedance calculations, we still use one number, but if you really dig into it, you'll see it'll go between there. So the higher the resin content, the lower the dielectric constant, but it'll also have a higher dissipation factor for higher resin parts. Typically, thicker cores have higher resin content than thinner. Prepregs vary as well, and the vendor may very well mix the different types of prepregs together to achieve the desired layer-to-layer spacing. So then you even wind up with different numbers. This is why I really, drill into you. It's like, okay, when you do a prototype board, you might not want to be calling out specific materials because of the drawbacks of that. But once you're done, you can demand from the vendor that you can get the stack up for future revisions, and then supply that stack up and say, build this exactly the same. You give us two different engineers the same print, we might very well build it slightly different. We'll still wind up with the layer-to-layer spacing being the same, but we might adjust the prepreg a little bit differently, use different types of prepreg to achieve that dielectric, that layer-to-layer spacing. And so we really encourage you to say, okay, ask for the stack up of, okay, how do we build this board? At Royal, we'll be more than happy to supply, say, okay, this is exactly how we built it. It'll show 2 sheets of 1080 between the 2 layers. And then you provide that in the future when you do, as you're still tuning the board, and that eliminates any source of confusion or error or uncertainty of, okay, you go to a different vendor and they say, okay, we don't have this in stock. We'll substitute this in its place. So, even though you've got one dielectric constant for material, it does vary within that material. And the easiest way to solve that is to demand a stack up from the vendor. As I said, at Royal, we'll be more than happy to provide it for you before or even or after the board. We'll often send a layer stack up to the designers for approval once we've decided what material we have on hand and what we think will work best for their design. Two common types of high-speed material are FR408, which would be from Isola, and Nelco 4013. They both have a lot of the same properties, but they still act very differently within your design. Itera is one we've started to use. It's kind of nice because it's very stable over a big frequency range, and it's suitable for both high speed as well as high frequency. But of course, it's expensive and much longer turnaround time. High frequency boards, of course, are for RF designs. They usually have low DF and very consistent dielectric constants within that group. Generally with these hybrid boards, generally with these high frequency boards, they'll be done as hybrids with one piece of Rogers laminate and the rest FR4. Ceramic RO4000 is a common one, and you'll mix that. That's from Rogers, of course, and so you'll mix that with FR4. You'll have a cap of Rogers, and then the inner layers will all be FR4. You've also got the Teflon-based 3000 series from Rogers, as well as Taconic, and these are really good for. They are often used in wireless assemblies and can be done in double-sided or composites with FR4. Itera is also used within high-frequency designs as well. Polyamide is a good old reliable one that's been around forever. It has a very high glass transition temperature and low coefficient of thermal expansion used in high temperature applications. Back when I was in aerospace, we used this exclusively. Polyamide, Isola P96 and the Nelco N7000 are good examples. They're very chemical resistance. They survive very good in different assembly applications, including lots of rework. That's why we liked it. Obviously, we would often rework the board extensively as we kept swapping out components. But there are a lot of drawbacks. It's brittle, and the big thing is it is very good with absorbs moisture very well. So it really sucks it in. So there's a lot of handling issues as well as storage issues with polyamide. So it's not always the best solution, but it is one if you're dealing with some extreme environment stuff. This table just shows a lot of the sample properties of the different flavors of laminates. FR406 from Isola is kind of one of the lowest of the suitable for lead-free. The SNL4 from Nanya is what we use for double-sided that don't require high glass resistant temperature, so for non-lead-free applications. 370HR or 185HR from Isola is what we use for all multi-layer boards, whether you specify lead-free or not. We just do it there. So you can really see that that everything is fairly consistent within the range. The lower factors of the dielectric constants for the high-speed materials, different from the 4 of the regular FR4. The higher speed Rogers down around 3. So then the last thing, of course, is on how you want to call them out on a board. You can call out by property, like saying specify a specific dielectric constant or glass transition temperature. But the trouble with that is it's not very specific, and two very different materials might have the exact same property. IPC slash sheet is very common, but of course the trouble with that is then you can have a lot of variety of you have a big variety of properties within that slash sheet. So you go to different vendors, call out for the exact same slash sheet, you might get two different materials from two different suppliers. Probably the best and most accurate is calling out the specific material. Of course, then the trouble is your vendor might not carry it. Often what we'll see is you say HR 370 HR or equivalent. That tells us that, okay, it's going to be for a lead-free application. We can use it for we can go ahead and use 185 of HR for it as well. Getting back to what I said earlier, if you're dealing with high speed or high frequency designs where it really is, then you're calling out the exact material and the supplier often for it. And that's the importance of getting the stack up from the vendor when you do a revision to the board, so you can say, okay, let's make sure we build it the exact same way. Feel free to work with us. I know we do this all the time. We send out stack ups to the customer saying this is the material we're going to use. I spent an hour on the phone a week ago with someone going over a board that they're using Itera material on. We went through layer by layer saying, okay, exactly what we're going to use for it, and we looked up the dielectric constant for each of the specific thicknesses of the material we were going to use just to make sure it fit into his design. At the end, I gave him the stack up, so that will always travel with no matter when the design's revised with it. And then the other advantage of when you're working with a vendor is you can find out, okay, what's the lead time? Itera, it takes us about a week to get the material. It's really expensive, so we don't carry a huge variety on hand. For all the standard HR 370 materials, we'll have a huge variety on hand. Even the high-speed materials, the basic 408, will have a few varieties, so there's no slowdown. But if you start calling in some ceramics or some specific Rogers, and you've got a specific deadline date, call us, work with us during the design phase, and we'll get the material on hand. So when you're ready to place your order, we can do that for you. So, as I said, this was a really generic, high-level overview of materials, and when you go into your specific design, you really could go into each one and spend a good amount of time. If there's any questions, I can try to answer some of them. Feel free at the end. Here's my email address. I can give you my phone number, and we can go over some of the stuff. If I can't answer it to you, we've got contacts with all our suppliers. It's no problem. We'll get any more additional information you might need. So that's all I have today, Lisa.
All right, thank you very much, Tim. I am open up here. If anybody has questions, please go ahead and submit them in the question box. And I know some of the questions may be a little hard to answer in a group format like this, so if that's the case, Tim will definitely get back to you. We will also have a copy of our free white paper that will have all of this information in it. Please email Tim a copy of that, or you can also visit our website and we'll have a copy of this presentation as well as the paper on there. All right, it looks like we are good. So thank you everybody for attending, and we look forward to working with you soon.